Hello there. In the last video we derived a integral representation for the fractional derivative integral operator, and that was given by the expression derivative with left-hand point a, terminal point x of order minus alpha of some function of x f is equal to 1 divided by gamma of alpha times the integral from the initial to the terminal point x of x minus t to the power alpha minus 1 of f of t dt. And this expression is sometimes referred to as the Riemann-Liouville fractional integral. So in this video we're going to be looking at some properties of this RL fractional integral, which can be really used to actually solve some fractional derivative problems. Alright, so before we actually move on to a couple of these properties, let's just mention a couple alternative notations for this representation. So since we're usually talking about integrals when we're working with orders of minus alpha, sometimes it's useful to write this as another operator, say I, with endpoints ix of order alpha. So this definition is equal to 1 over gamma alpha times the integral from a to x of x minus t alpha minus 1 f of t dt. So this is going to be useful, so this is going to be valid for any x value greater than a. So if you want to find the fractional integral of this function at, say, x is equal to 5, a has to be less than that, say 0 or something. So if you want the opposite direction, so ixa of alpha of f of x, this is going to be equal to 1 over gamma of alpha times the integral from x to a of x minus t alpha minus 1 f of t dt. So this is going to be the definition valid for any a less than x or a greater than x. Alright, so these are the two, or I guess you could think of it as one, definition of the Riemann-Liouville fractional integral, which we actually derived from a modification or generalization of the Grunwald-Litnikov representation. So let's actually work on an example of how to calculate the fractional integral of a particular function. So let's find the fractional integral, the half fractional integral of x cubed, and let's assume we just want the general expression for that. So by definition, that's going to be equal to 1 divided by gamma half times the integral from 0 to x of x minus t to the power minus 1 half of t cubed dt. So since this right-hand integral is a function of x, then this of course gives you a general representation of x cubed, and if you're really clever, maybe you can even find a general expression without having an integral here. But of course, the theory of integrals usually implies that a lot of these functions actually do not have closed forms in terms of elementary functions, so there is some difficulty there. So let's actually find the half integral of x cubed at a particular point. So let's find the half integral of x cubed at, say, x is equal to 1. So this is equivalent to finding the half integral of x cubed from 0 to 1, which is going to be equivalent to gamma of 1 half times the integral from 0 to 1 half of x minus t, or x 0 to 1, not 1 half, of minus 1 half of t cubed dt. Alright, so what do we have here? So as we know, the integral from 0 to 1, when we have something along these forms, is almost like, wait a minute, why is that thing there? So this is supposed to be 1. So this function should look familiar. This should look familiar to be the beta function. So remember, the beta function of alpha comma beta is going to be the integral from 0 to 1 of, and depends on how you look at this, you can call this as t to the alpha minus 1 times 1 minus t to the beta minus 1 dt. So this is what we call the beta function of variables alpha, beta. So if that is true, then that means this is the same as writing the integral from 0 to 1 of order 1/2 of x cubed. This is going to be equal to 1 over gamma 1/2 times, so let's write this in beta form. So this is going to be t to the power 4 minus 1 times 1 minus t to the power 1/2 minus 1 dt. So this is going to be equal to the integral from 0 to 1, 1/2 of x cubed, which is going to be 1 over gamma 1/2 times beta 4 comma 1/2. So this is of course a number, and if you don't know about beta and gamma functions, then you can leave this as the closed form of the answer. But these actually are very easy values to get. So we know that the beta function is related to the gamma function via the relationship. This is going to be gamma alpha, gamma beta, all over gamma alpha plus beta. So we see that our gamma 1/2s cancel, which is very nice. And we know that gamma 4 is equal to 3 factorial. So this is just going to be I, 0, 1, 1/2 x cubed, which is going to be equal to 3 factorial, all divided by gamma of 4 plus 1/2. That's going to be equal to 9/2. So since the closed form of gamma halves is known, since that's related to the square root of pi over 2, one can find that this is actually equal to 105 square root of pi all over 16, once you use your properties of gamma and gamma 1/2, which of course reduces to 32 divided by 35 root pi. So this is the fractional integral of x cubed at x is equal to 1. So definitely this, I've chosen a particular value that happens to work very nicely. But of course, if you choose any other number, say x is equal to 2 or x is equal to 3/2, or any arbitrary x, definitely the process is a little bit more difficult. But most of the time, you can usually use like numerical software like MATLAB to approximate these values. So let's look at a couple more properties that may be able to help us out in calculating some of these things. So one can prove that the fractional integral with terminal points ax of order alpha of some constant times a function is actually just equal to c times the fractional integral from a to x of alpha of the function f of x. So this sort of mirrors the standard properties of integrals and derivatives, which isn't too bad. Also, it's easy to prove as well that the fractional integral from a to x of alpha of f of x plus or minus g of x, we're assuming f and g are integrable on some interval ax, is going to be equal to the fractional integral from ax alpha of f plus or minus the fractional integral of ax of order alpha of g of x. That's also an easy proof to go through in case you're interested. That proves that the fractional integral is a linear operator if you combine those two properties. The property 3 is a little bit more interesting and extremely useful, and that's the composition property. So the fractional integral from ax of order alpha of the fractional integral of from ax of order beta of some function of x can actually be interchanged. So you can write this as alpha beta or beta alpha, and this is actually just equal to the integral from ax of order alpha plus beta of the function. And this property actually is true for just standard integrals and also standard derivatives. So finding the second derivative, finding the third derivative, and composing them actually comprises the fifth derivative. And you can do that in any composition that you want, as long as alpha, beta sum up to those values. All right, so let's go through a proof of this because this definitely has some interesting characteristics in it. All right, so let's do ax alpha of ax beta of f of x. So let's start off by focusing on this interior expression. All right, so this is going to be equal to, so let's take the fractional integral of alpha of this function in the middle. So that's going to be 1 divided by gamma of alpha times the integral from 0 to x of x minus t to the alpha minus 1 of this function that we're taking the fractional integral of. So that's going to be the integral from a to some dummy variable t of order beta of f of t, and this is an integral in terms of t. make sure you get your variables of integration straight there. All right, so now we can represent this fractional integral in terms of the standard integrations that we know this to be. So it's going to be equal to 1 divided by gamma alpha times the integral from 0 to x of x minus t alpha minus 1 times, then we have 1 over gamma of beta times the integral from a, or 0, to t. Actually, that should be a, not 0, in general. And that's going to be, so let's switch our variables to, say, psi. So t minus psi, beta minus 1, f of psi, d psi, dt. All right, so what do we have here? So we have 1 over gamma alpha, 1 over gamma beta. Those are both constants. We have some integrals here, and we can sort of rearrange our integrals using our standard Calc 3 tricks. So this is just going to be equal to 1 over gamma alpha, gamma beta. And then we have the integral from a to x of the integral from a to t of x minus t alpha minus 1, t minus psi, beta minus 1, f of psi, d psi, dt. Alright, so what can we do with this? So you may observe that these two expressions here in parentheses are almost the same exact thing. If you look in a very naive way, you can pretty much see a minus t here and a t here. So you may even consider of expanding alpha minus 1, beta minus 1 in terms of natural numbers, then extending that to the real numbers via whatever method you have, namely the general binomial theorem. And then you can see a lot of cancellations or combinations that you can actually perform on this expression. So I'm going to be focusing on these two expressions, and I'm also going to be focusing on the variable dt, because the only thing that actually has psi in it only is going to be f of psi d psi. Alright, so once I expand these two things via substitution and some shift theorems, then you can actually rewrite this as the integral 1 over gamma alpha, gamma beta, times the integral from a to x. This can actually be written using substitutions as the integral from 0 to 1 of x minus psi alpha plus beta minus 1 times 1 minus u alpha minus 1 u beta minus 1 f of psi du d psi. So once we have that, now we can rearrange this in terms of the variables that we actually care about. So we have 1 over gamma alpha, gamma beta. That's not a gamma, that's not an f, that's a gamma. And then we have, this is going to be equal to the integral from 0 to 1 of 1 minus u alpha minus 1 u beta minus 1 du, multiplied by the integral from a to x of x minus psi time to the power alpha minus beta plus alpha plus beta minus 1 f of psi d psi. So as we know, this is the beta function of alpha beta. So this is just going to be equal to 1 over gamma alpha, gamma beta, times beta of alpha beta, and then times the integral from a to x of x minus psi alpha plus beta minus 1 f of psi d psi. So using our properties of beta alpha plus beta, this is actually just equal to gamma alpha, gamma beta all over gamma alpha plus beta. So gamma alpha, gamma beta product cancels. So we're just going to be left with 1 over gamma alpha plus beta times the integral from a to x of x minus psi, or you can say x minus t. There's no real, doesn't really matter because psi is a dummy variable, so we can call this as x minus t alpha plus beta minus 1 times f of t dt. And this is precisely the definition of the fractional integral from a to x of order alpha plus beta of the function f of x, which I think is a very beautiful result. So with all these properties, let's pretty much outline what we have here. So summary. And this is for the Riemann-Liouville integral. There are other integrals such as the Caputo different integral that we'll discuss later, which these definitions need not necessarily have the same exact properties as one another, which actually creates some people say difficulty with fractional calculus, because some operators have different properties than others, which makes some more advantageous than some others. So of course, the Riemann-Liouville integral satisfies these properties. The integral of ax of alpha, cf of x. As we said, the constant can factor out, so we have this property. We also have the linear property, so we can rewrite this as just EAF alpha plus or minus IAX alpha g of x. And this third property, which is very, very useful, so IAX alpha of IAX beta of f of x is equivalent to finding EAX beta of IAX alpha of f of x, which is just equal to IAX alpha plus beta of f of x. So combining these properties, there's one important observation that we need here. So one only needs I alpha well defined for alpha between 0 and 1, and d alpha well defined for alpha between 0 and 1. To me, even though this is not really a theorem, more so a corollary, this is an extremely powerful and useful observation. So let me sort of demonstrate what I mean here. So for example, let's assume we want the 3-point second derivative of some function f of x. So, and we can define d to be, say, the Grunwald-Letnikov derivative, for example. So we can rewrite this as d of 3 of d of 0.2 of f of x. Now, even though d can be defined as the Grunwald-Letnikov derivative, remember, this is just an extension of the classical derivative from standard calculus. So this is just precisely equal to the third derivative with respect to x of the Grunwald-Letnikov derivative of order 0.2 of f of x. So as long as you can find any order between 0 and 2, then that is actually perfectly fine. Now this is not the only way that you could do this. So let us assume we still are interested in the derivative of this. So we can actually rewrite this as d 4 times d of, let's say, negative 0.8 of f of x. So this is just equivalent to writing d4 of I of 0.8 of f of x. So this is just, say, the Riemann-Liouville integral of f of x, and this is just a classical order derivative of order 4. So this is the fourth derivative with respect to x of the Riemann-Liouville integral of order 0.8 of f of x. So that gives us those two alternatives. So the other direction, for example, let's assume we're interested in the 1.5 integral of f of x dx. So what we can do is we can rewrite this as I of 2 times d, or I of negative 0.5. That's one way to do it. But of course, I of 2, so I of negative 0.5 is the same as d of 0.5 f of x. So here, as long as the order of our integral is a natural number, this is just the double integral of the Grunwald-Letnikov order of order 5, of 0.5. So that's no big deal. So this is just pretty much like the integral from 0 to x, of the integral from 0 to x, of the GL derivative of order 0.5 of f of x, dx dx. So that's pretty much all that is. But of course, that's not the only approach one can do. So I of 1.5 of f of x can be found by, say, doing I of 1 of I of 0.5 of, say, f of x. So I have 1, since that order is a natural number, we can just treat that as a standard derivative, or standard integral rather. And I 0.5 can be defined as the Riemann-Liouville integral operator. And that would just be that. So this at least shows us that as long as we can find fractional derivatives and fractional integrals of any order between 0 and 1, we can actually pretty much use the classical calculus and any results from there, and then use our extensions to the fractional realm to fill in any of the missing pieces in between. Now, of course, the types of integrals and the types of derivatives that you actually use in these extensions possibly can give different results. And of course, there is some debate on which one is best because, for example, factorial can be extended by the gamma function, but it's not necessarily the only function that extends the factorial function. So it may not be the best, maybe it is, we don't know. But we'll discuss these questions in the upcoming videos, of course. But anyway, I hope this gives you some insight of some of the properties and some of the shortcuts that you may want to use when finding fractional integrals and fractional derivatives of functions.